So let's talk about the last major Chem 2 topic that we're going to encounter. Right? And that's electrochemistry, often called oxidation reduction chemistry, or redox for short in the chemical circles. It is actually combines a lot of different topics that we encounter. Thermodynamics, equilibrium, and kinetics. So those three topics together play major roles in the practicality of redox chemistry. Now, we're going to show where those show up, not the kinetics so much because that's more of an advanced topic, but definitely the thermodynamics and the equilibrium play a role in redox chemistry. Electrochemistry, as the name implies, involves a lot of transfer of electrons. Some would even say that all of chemistry is just electron transfer. All right? So you could sum it down: electron transfer or proton transfer, or both. All right? So it is a major idea in the chemical world. All right? But let's go back to chemistry. All right, let's go back to Chem 1. All right, and one of the very first things we did in the lab, all right, was we dropped a bit of zinc into copper. And if you think about what happened, is something changed. So if you take a look, we have this zinc metal, this big bar of zinc, and we have copper ions that are these blue ions in solution. And we place them into solution, and you get a change. All right, so we've dropped the two in there, and all of a sudden this zinc starts to change. You've all done this reaction. Every single one of you has done this reaction, or mostly. All right, so if you think about it, if you remember, that black fuzz that grew on the zinc was not actually black. It was brown. Okay, it is a brown copper-colored material, and the reason for this is it is copper. It is copper metal. All right. So what happens is the zinc here changes the copper back into copper metal. All right, you can see this. All right, one of our physical changes is a change in color. Rapid changes in color usually denote some sort of chemical change. All right, again, all the way back to Chem 1. So we're coming full circle again, all the way back to the first couple of days of Chem 1. So the copper ions, copper plus 2, has now become copper metal, Cu. What's happened? All right. The copper has gone from copper plus 2 to copper that is uncharged. So that plus 2 charge has been eliminated somehow. Right? And what's happened in that case is that somehow that copper plus 2 has become a copper with no charge. And the way it's done that, it's gained 2 electrons. Right? Those 2 electrons have neutralized the charge, so to speak, balanced out the charge. It actually isn't balanced, it isn't actually neutralized. Those 2 electrons are formally transferred to the copper. Right? And so that represents a change in the number of electrons in the species. Now what's interesting is that, again, one of the things we talked about in Chemistry 1 and Chemistry 2 is that if the forward, I guess this, let me see, I wonder which way am I looking at. So if the forward reaction, I think it's pointing this way, if the forward reaction is spontaneous, which it is in this case where you drop the zinc in, that means the backwards reaction is not. That's a hallmark of spontaneity. Again, goes back to thermodynamics. So there's a Gibbs free energy relationship here. The forward reaction is spontaneous. That means the backwards reaction is not. And so if you try this with copper and zinc, you put the copper into the zinc solution. Instead, you don't see any reaction. You don't see the copper dissolve in that process. Right? So that's important. That's an important observation that we see. All right? So the zinc is what's transferring the electrons. All right? So those two electrons have to come from somewhere. What we don't see is that the zinc is becoming zinc ions because they're colorless. And you can actually see that in this one. The copper blue color goes away, the zinc ions show up in solution. And you can actually observe those by measuring the amount of zinc in solution as a function of time. But the reverse reaction does not happen. Copper and zinc, copper metal does not react with zinc, right? So we're going to talk about why that is during the course of this lecture, right? Well, not this lecture, but this module. Right? So electrochemistry, in short, looks at the factors that influence the transfer of electrons between species and the resulting change in charge and mass balance. It builds on Gibbs free energy, we talked about, whether or not it's a spontaneous transfer of electrons or a non-spontaneous transfer of electrons, and how we can alter the spontaneity based upon equilibrium and non-equilibrium conditions, plus acid-base chemistry. Some things are really reactive in acid, some things are not. Again, these are ideas that we've all touched on throughout the course of the semester. All right? So, lots of shifting pieces, but you have tools at your disposal for each of these. Electrochemistry is a primary component in quantitative analysis and very important in biochemistry as well. All right. But before this, we're going to have to talk about one general chemistry topic that we hit on for maybe a day in Chem 1, but we're going to use heavily this class, and so it's worth reviewing. Right? And that is the concept of an oxidation number. An oxidation number is a formal way of relating how many electrons an element has gained or lost compared to its native state. All right? By that I mean elements in their pure form under standard state conditions, how many electrons they have, and how many they gain or lose. A lot of this is related to electronic structure, right? But we're not going to necessarily rely heavily on the electronic structure arguments. Oftentimes we're going to infer what the charges or the electron counts are from other bits of information. But here's the thing. We have already been doing this. This goes all the way back again to, surprise, naming. All right? So, all right, we can identify the oxidation number for an element based upon what its electron count is. In general, oxidation numbers of a pure element are 0. So fluorine, F2, off the periodic table is a 0. Oxidation numbers of ions are typically the same as the charge. So an iron that's +2, such as these two irons, we would call that an iron 2 or an iron +2. Its oxidation number would be +2. And we typically show the charge sign. Charge of a monoatomic ion and oxidation number of a monoatomic ion are the same. Let's harken back to one of our exotic ions. Remember mercury 1 cation, Hg2 +2. All right. Each of those mercuries had a +1 charge, so the oxidation number of each of those mercuries would be +1, even though the total charge is +2. And the reason for this is it's not the charge, it's the oxidation number. So in this case, the copper goes from +2 to copper 0. And so the oxidation number here is +2, the oxidation number here is 0. And so to go from +2 to 0, you have to gain that many electrons. And so charge and oxidation number are pretty closely intermingled. but you can apply it to things that are not formally charged. All right? In some ways, we pretend like it's charged. It's gained this many electrons. Right? And in many relationships, it is tied to the most stable form of the element when it's charged, but not always. Typically, we can assume the following. We can usually infer the charge of everything else if we keep in mind these simple things. The oxidation number of a hydrogen is usually +1. The oxidation number of an oxygen is usually -2. Right? Now, we could take a look at something like water. HOH. This is formally a covalent compound. This is covalent. We don't think of it as O-2 and H plus and H plus. All right, this is not an ionic compound, but in electrochemistry, we can pretend. All right? We can pretend like the hydrogen has a +1 charge and the oxygen is -2 charge. This oxygen formally has 8 electrons. This hydrogen formally has 2 electrons. Right? But in terms of oxidation number, the hydrogen is deficient an electron compared to elemental hydrogen. And so it is a formal way of recognizing things. Now, in general, the oxidation number for multiple elements in the same compound will not differ. Something like Fe2O3, both of these ions have a +3 oxidation number. Right? And we usually show the sign for the oxidation number the same way we do the charge. Right? Now, for compounds, a neutral molecule, the sum of the oxidation numbers is 0. The sum of the oxidation numbers is 0. And for an ion, the sum of the oxidation numbers equals the charge. In some ways, you can use this to figure out the oxidation number for each thing. Now, we've been doing things like this already. Again, it goes back to naming. Cr, CO3. This is chromium carbonate. This is actually not chromium carbonate. This is chromium 2 carbonate because we know that the carbonate has a -2 charge. The chromium has a +2 charge in this case. But we can dig in and figure out what the oxidation number of each of these species is by pretending that we know the oxidation number of each of these oxygens is O-2, and so there's a +6, +2, so the carbon has to be +4 oxidation number. Okay? So each of these oxygens has the same oxidation number, -2 each. And so if we're counting up changes in electrons, we have to look. Electrochemistry looks at changes in the number of electrons gained or lost by compounds and species. So we pay attention to them. On top of that, the metals are really flexible, so look there first. All right? That's a first quick, not always, but the metals, this is why we define charge for the metals when we name them. It's because they can be really flexible in their oxidation numbers. Okay. So let's take a look at an example. HF, again, we can pretend it's ionic, even though HF is not ionic. It's a gas. Ionic compounds are not gases. We can pretend that the fluorine has a -1 charge, an oxidation number of -1, and we can talk about the hydrogen has an oxidation number of +1. Together, they charge, total charge is 0. The total oxidation number count is 0. Right? And this plays out in the chemistry of the species as well. Right? Ammonia, on the other hand, we could conceptually imagine it as an H plus, an H plus, and an H plus attached to an N minus 3. And so the oxidation number of the N is -3. It isn't, but that's a conceptual way of imagining it. All right, and so we could talk about how the oxidation number of the nitrogen ammonia is -3. All right, so let's try it for each of these. My suggestion is do it along with me. So let's look and then hit pause before I get to the answer. So let's take a look at MnO2. All right, so the name for this would tell us the charge on the manganese, and the oxidation number should fall out from information on the periodic table. Okay? Now, except for the transition metals, you can't know what those are. In general, unless it's oxygen, fluorine, or hydrogen, you have to infer the charge from other information. So let's look at MnO2. Oxidation number for the manganese is +4. All right. So this is a manganese 4 oxide manganese. This is a manganese 4 oxide, so the manganese has a +4 charge. So the manganese has a +4 oxidation number. Let's look at the manganese here. This is permanganate, MnO4 minus. There's a minus sign right here. This material, oxidation number is +7. MnO4 minus. Each of these oxygens has a -2 oxidation number, and there's 4 of them, meaning that all of the oxidation here is -8. If you sum all the oxidation numbers, again, the oxidation number of the oxygen is not -8, it is -2. Right? And the only way you can still have a negative charge, again, the sum of all the oxidation numbers has to equal the charge. If this was neutral, it'd be easy, but it's not. This is +7. Okay? So the oxidation number of this permanganate is +7. Sorry, KMN. And you can see this even in something like KMNO4, where this is a +1 charge. It's a potassium ion. Right? This is then the whole thing right here would be a -1. Again, the same idea applies. -8 for each of these ox total. So this is O has a -2 oxidation number. The manganese has a +7 oxidation number. All right. So that would represent the oxidation number of the species here. We could do the same thing for the chromate here and the chromium and dichromate. Survey says +6. So this is chromium 6. And there's 2 of them. All right, so there's 14 for the oxygens, 14 electrons negative for the oxygens, and 12 electrons negative for the chromiums, split over, 12 positive charges for the chromium, split over 2 chromiums for a +6 species. Right. This would be a +6 as well. For this manganese, this is the, this isn't permanganate, this is something else. I don't know what the name of this one is. Supermanganate, I don't know. All right. And last, this sulfur would be oxidation number. Well, this one is +6. This one has to be +6 because everything else is the same. Right? This is a +6 for the sulfur. Right? And this one, though, would be a +4 oxidation number. Okay? Prove that to yourself for each of these. Okay? Once again, chemistry of redox changes involves changes in oxidation number and changes in electrons. Okay. More practice. Let's run through these real quick. Again, I do highly recommend that you pause. I will let you chew on it, and then I will state the oxidation number. All right. So here's NH3, and we covered this one a few seconds ago. Oxidation number for the nitrogen is -3. Each of the hydrogens is typically +1. There's 3 of them, -3. All right. Let's try this N2H4. Going once. Going twice. Third time's a charm. Each of those nitrogens would have a -2 oxidation number. All right. +2, +1, +1, +1, +1. So this is +4. Each of these would have to total that -4. So each would be -2. This nitrogen here, N2, 0 oxidation number because it's nitrogen in its native state. All right, so watch out for these. Right? Elements off the periodic table, 0 oxidation number. All right. Now let's try the other side of it. Here's O-2. Again, mostly you can choose, accept that oxygen is going to be -2, excuse me. So that means that the nitrogen is going to be, each of these is going to be +1 oxidation number. Now here's one that's a little hard, but I'll let you chew on it. This nitrogen has to be -1 oxidation number. +1, +1, that's 2. The hydrogen, +3, all right. Oxygen is typically -2, leaving a +1 charge that needs to be compensated for, so this nitrogen would be a -1 oxidation number. All right. This nitrogen, going once, going twice, +2 oxidation number. Here's a +3 oxidation number. Here's a +4 oxidation number. Here's a +5 oxidation number. Okay. So nitrogen in this case can have a range of oxidation numbers from all the way from -3 up to +5. And this is just a handful of examples for nitrogen. So the oxidation number doesn't come from the periodic table, it comes from our observation of the materials. And to form these compounds, you form them different ways. And so that means that these materials have different capacity for absorbing electrons or typical donation ability for forming electrons. All right? So review your oxidation number chapters, look up oxidation number or redox in your textbook. All right? So this is the starting point for any redox reaction. If you cannot find the oxidation number, you will get everything else wrong. So this is one of the skills that you want to demonstrate. Determine the oxidation number for an element.